Mercury, the tiniest world and nearest to the Sun among all planets, pushes the boundaries of natural extremes in scarcely conceivable manners. Daytime highs can reach 430 degrees Celsius, intense enough to liquefy metals, while nights drop sharply to minus 173 degrees Celsius, frigid enough to solidify iron. Beyond these swings, the planet bears scars from the solar system's formative era, etching the brutal principles of the cosmos. It's made up of 70% metal, its dense core accounting for roughly 85% of the overall diameter, rendering it among the densest bodies in the system. Mercury's secrets deepen further upon learning of its sodium tail, extending nearly 2.5 million kilometers, an unseen trail detectable only via cutting-edge instruments. Yet, this is merely the start. Let's venture deeper into Mercury's domain, hailed as the solar system's harshest environment. We've noted its wild thermal fluctuations, but the contrasts extend beyond, defying fundamental physical principles. Herein lies Mercury's premier enigma, perhaps its most profound, an unmatched thermal oscillation. Picture it. Over a single day-night cycle, surface heat surges to 430 degrees Celsius, capable of fusing metals, then crashes to minus 73 degrees Celsius, surpassing Earth's chilliest evenings. This staggering 600 degrees Celsius gap stems straight from the planet's virtually absent atmosphere. Lacking any substantial air layer to hold warmth, sunlight's energy gets absorbed and promptly released into the void as darkness descends. Indeed, Mercury boasts next to no atmosphere at all. That scant gaseous envelope fails to capture solar warmth. Then how does ice persist amid such brutal conditions? Radar observations from Arecibo Observatory uncovered an oddity. Permanent water ice lingers at the poles. Sunless pockets in deep polar craters form zones of endless shadow, keeping temperatures locked in ice despite the surrounding blaze. These spots function as innate freezers, safeguarding water for eons without thaw. Experts suggest long ago comets or cosmic impacts delivered moisture into these shadowy depths. How then does a near-airless Mercury retain liquid in such hidden spots? This puzzle transcends mere frozen water. It probes life's potential beginnings across the solar system. If shadowed craters on Mercury safeguard ice, might future probes detect organic hints within? Similar to water signs on far-off worlds, this icy presence defies expectations. Still, probing it demands conquering an even steeper hurdle. The sun's unyielding tug. Reaching Mercury demands warring with gravity itself. Entering solar orbit ramps up a probe's velocity amid the sun's colossal pull, which accelerates vessels at breakneck paces. One of the mission's toughest feats. Such force is fierce. Absent braking maneuvers, the craft would hurtle beyond Mercury straight into solar doom. This unforeseen snag complicates any venture toward the world. BP Colombo, the probe now en route, must traverse 8.5 billion kilometers. Far from a straightforward jaunt, it involves a grueling trek with 18 solar loops and 9 slingshots past bodies including Earth, Venus, and Mercury. Why the circuitous route over a straight shot? Blame the sun's gravitational dominance. For braking, Pippi-Colombo devised an ingenious tactic, veering off course to borrow planetary gravities, dialing back the spacecraft's velocity. Ion propulsion tech proves vital along the way, firing steady blue light for subtle propulsion that keeps the craft from solar capture en route to our star's innermost neighbor. Still, that's not the sole key to Colombo's triumph. Nearing Mercury exposes it to solar radiation tenfold Earth's dose, so Beep Colombo sports a sophisticated ceramic heat shield. Built to endure blistering heats unscathed, it safeguards vital parts like research gear and comms arrays. The ceramic heat shield plays a vital role in shielding the spacecraft from these impacts, while also ensuring that the scientific equipment stays at a consistent temperature without getting too hot. Yet, the difficulties extend further. Bepi Colombo must dodge not just the blazing solar heat, but also the wild swings in temperature across its path. The elongated path of Mercury around the Sun creates a major hurdle for keeping the spacecraft's heat levels steady. Bepi Colombo depends on clever flight paths to preserve its functionality and prevent thermal overload. Could there be a method to hold a constant temperature without needing such an intricate setup? Bepi Colombo, leveraging cutting-edge tech and intricate flight maneuvers, offers a short-term fix, yet it's merely the initial phase in probing and overcoming the tough environmental barriers of outer space. Given today's tools, venturing to Mercury stands as one of humankind's toughest feats. Mercury isn't simply a world hugging the Sun. It serves as a unique testing ground where physics principles appear inverted. Hidden deep inside Mercury is a structural feature that bucks the trends of typical terrestrial worlds. Picture a small body boasting a metallic heart, comprising 85% of its width, rendering Mercury the second most compact planet in the solar system, surpassed only by Earth. What accounts for Mercury's enormous iron nucleus? Fresh analyses, especially those from the Bepi Colombo probe, are shedding light on the planet's inner makeup. Readings from the Bepi Colombo craft show that the metallic center isn't a mere solid lump. It remains warm, suggesting the world hasn't entirely chilled since birth. A leading idea about Mercury's beginnings is the massive strike concept, positing that during the solar system's infancy, it suffered a tremendous smash-up. That event stripped away much of Mercury's outer rocky layer, exposing a thick, weighty iron interior. Ongoing investigations uncover an unexpected detail. In the Sun's youth, its intense emissions could have stripped away lighter elements from the surface, sparing just the metallic base below. This recent finding aids our grasp of how worlds form in our cosmic neighborhood. Yet another puzzle experts are tackling is Mercury's gradual contraction. Vast fissures on its exterior, such as the Beagle-Ruppes escarpment, indicate the planet has dwindled by more than 14 kilometers over its lifetime. This implies the iron core keeps cooling and tightening progressively. Researchers think that as the core loses heat, the whole body compresses and splits. These splits, or lobate scarps, provide stark proof of past, notable tectonic shifts. Still, aside from the contraction, a topic sparking arguments among experts is the presence of vitality inside Mercury. The enigma of its iron core persists as a tough nut to crack. How has Mercury sustained a molten iron center across eons? And can examining the shifts in its core truly unlock the architecture and development of this world? We used to view Mercury as a desolate, sun-baked realm, pocked with craters and utterly still, akin to a warped lunar stand-in. But might this quiet be the biggest myth in planet studies? Revelatory findings from key probes, the NASA Messenger Orbiter and the fresh Bepi Colombo effort, a joint venture by Europe and Japan, have exposed a shocking truth. In the solar system's early light, Mercury wasn't just seething. It has harbored an inner blaze much longer than anticipated, turning it into a dynamic record of planetary reshaping. Begin with Caloris Basin, an enormous strike pit spanning 1,550 kilometers across. A surface wound about the scale of Texas, long regarded as prime proof of the solar system's late heavy pounding. But is it merely a basic hole? High-res photos disclose Caloris as far more than a depression. It's an ancient, solidified, molten expanse. Even more crucially, at its heart sits an odd, profound web of rifts, dubbed Pantheon Fossae. Resisting standard interpretations, these rifts fan out from a pit close to the middle, Apollodorus. Experts posit the impact's violent energy generated a pressure pulse that raced over the globe, cracking the thin shell and letting deep-seated melt rise to flood the depression, forming the even terrains visible now. Prior to the insights from the Messenger mission, experts assumed that Mercury's volcanic processes had halted billions of years in the past. Yet studies have pinpointed areas featuring level, glossy expanses coated in a glossy layer, displaying minimal tiny craters, indications of fairly recent lava outflows that wiped out prior geological features. In particular, the finding of massive volcanic blasts independent of asteroid strikes like those at Novoi Mons has proven transformative. Such events happened as volatile substances, deemed unlikely on a world orbiting so near the Sun, were warmed by rising magma and blasted outward into the void, carving out depressions or fissures on the surface. More lately, investigations have revealed icy formations, resembling salt glaciers within polar craters in the north, such as the striking dual-ring basins of Rachmaninoff and Rotted Ladi. Experts in planetary geology suggest these features go beyond mere salts, potentially harboring additional volatile elements locked away and safeguarded for eons below ground. This breakthrough utterly reshapes our view. Though the planet's exterior endures furnace-like intensity, its hidden depths could offer greater potential for habitability. Might these salt glaciers, safeguarding vital life-building chemicals, foster a sheltered zone able to support an enigmatic type of microbe far below the surface? Protected from solar flares' blistering warmth, much like the moon, whose barren face Mercury echoes in appearance, this world has unveiled a far richer and more active past in terms of geology. Traces of its primordial inferno endure vividly as solidified lava oceans, rift-like breaks in the crust, and remnants of colossal volcanic outflows. Once a blazing inferno itself, what mechanism has enabled Mercury to retain sufficient internal heat within its enormous metallic heart, posing one of the solar system's biggest enigmas? Is the answer its magnetic field, once dismissed as unfeasible given the world's compact dimensions and extreme warmth? Probes such as Mariner 10 and Messenger have transformed our grasp of this enigmatic orb. Indeed, Mercury possesses a magnetic field, albeit a faint one, measuring just roughly 1.1% of Earth's strength. This revelation stunned researchers, since models predicted that a diminutive body like this couldn't generate the power needed to uphold such a feature. The field exhibits lopsidedness, with its magnetic axis shifted by 20% away from the planet's geometric midpoint, an unparalleled oddity among all magnetized worlds in the system. What accounts for this displacement? How does it produce a field so uneven, distinct from every other celestial body known? The process driving Mercury's magnetism relies on the dynamo effect, driven by swirling liquid iron in its interior. In contrast to Earth, where a substantial mix of solid and fluid core material produces a robust field, Mercury boasts a vast fluid iron core, yet falls short on vigorous power inputs. Theorists propose that gravitational pulls from the Sun provide the vital spark to sustain this field. The planet's oval path around the Sun produces ongoing tidal distortions which agitate the metallic depths, sustaining the liquid's motion and yielding a feeble but enduring magnetic presence. Among the most peculiar traits of this field is its skew. Not merely subdued in power, it's displaced to such a degree that it defies conventional geophysical frameworks. This peculiarity doesn't just test prevailing ideas. It unlocks fresh paths for exploring how planetary interiors operate. Does the skewed alignment reflect typical ways magnetic fields emerge on sun-proximate worlds? Or does it represent a one-off phenomenon? Even without an air envelope and with life-hostile conditions on display, the faint field could still enable key geological dynamics. Maybe, for all its frailty, it contributes significantly to equilibrium and shields the surface from cosmic interlopers. Though no match for Earth's robust shield, its mere presence might unlock profound revelations about the world's evolution and makeup, especially as Bepi Colombo and upcoming expeditions arrive. Surprises regarding the magnetic field could emerge shortly. The field's subdued off-kilter nature, combined with data from ongoing explorations, promises to deepen our comprehension of this elusive sphere. Past the field's subtlety, Mercury engages the Sun through interactions unique across the system. Devoid of a true atmosphere, it nonetheless sports a comet-like tail. Unlike Earth's protective blanket, Mercury's is essentially a wispy exosphere. This thin layer of gas endures relentless strikes from the solar wind, a flow of charged particles that dislodge atoms from Mercury's surface and hurls them outward into space. Within this exosphere, substances like helium, potassium, sodium, and hydrogen drift about, fostering an odd bond between the world and its star. Yet the truly astonishing aspect is the eerie sight of a luminous band, trailing millions of kilometers in Mercury's wake, transforming the planet into a gleaming, comet-like entity for all time. Known as the sodium tail, this radiant appendage can stretch as far as 2.5 million kilometers. Far from a mere solar wind effect, it stems from the pressure of solar radiation. Photons in the sunlight exert a force that propels sodium atoms away from the surface, forming the signature metallic streak. Such a process represents a profoundly distinctive physical dynamic. Although solar winds are known to strip material from planetary bodies, it's primarily the sunlight's influence that generates this perpetual extension from Mercury. What sparks this wonder? The photons emanating from the sun steadily drive sodium atoms into the void. Mercury, devoid of an atmosphere akin to Earth's yet sporting a metallic tail spanning millions of kilometers, exemplifies this. The relationship between Mercury and the Sun extends beyond mere erosion of matter. It uncovers deep repercussions from radiant energy and the planet's path. Far more than a sparse gaseous veil, Mercury's exosphere serves as the vital clue to deciphering the interplay between the planet and its sun. The mysteries etched on Mercury's surface are exclusive to this realm, offering the starkest proof that it upends notions of a dormant, unchanging landscape. This desolate, blistering orb sustains vigorous activity at the atomic scale. The Lobat scarp formations, with their radiating web of cracks, persistently test ideas about planetary geology. They stand as proof of the immense internal pressures from the planet's vast metallic core, which continue to warp the outer shell. Even amid brutal surroundings, this indicates a persistent, if gradual, evolution. Our quest to probe Mercury goes beyond mere intrigue. The Bepi Colombo mission aims to chart the planet's magnetic field and exosphere by roughly 2030. heralding major advances in probing its beginnings and development. Mercury evolves at a measured pace, safeguarding insights into the solar system's genesis. The geological and chemical imprints it bears aren't isolated occurrences, but vital tools for grasping life's origins and cosmic progression. Across Earth's long timeline, living organisms have weathered 5 great mass die-offs, each carving indelible scars on the planet's face. From the Permian event, which erased about 90% of ocean dwellers and 70% of terrestrial life, some 252 million years back, to the latest one around 66 million years ago, triggered by an asteroid impact that doomed the dinosaurs. How did existence rebound and persist amid disasters of that magnitude? Studies indicate that biology isn't just a series of chance happenings, but an intricate interplay molded by environmental and tectonic influences. Survivors tended to be those with remarkable versatility, able to thrive in unforgiving settings. Furthermore, remnants of enduring life post these upheavals often appear in fossils, showing that vitality invariably rediscovers paths to renewal amid the most dire straits. In the present day, consider these trials more intimately. Roughly 445 to 444 million years ago, our world confronted a crisis not born of scarcity in food or air, but from bitter chill. It marked the initial instance when life teetered on the brink of total freeze, as ice sheets advanced and seas withdrew. Prior to the ordeal, Ordovician Earth seemed secure and thriving. Worldwide temperatures averaged around 2 degrees Celsius warmer than now, with ocean levels nearly 600 meters higher than current ones. Vast portions of land masses lay under shallow, temperate, light-bathed waters, prime habitats for life's proliferation. Existence huddled almost wholly in the seas. Coastal margins turned into hotbeds of diversification, hosting early corals, brachiopods, mollusks, trilobites, and myriad other spineless creatures in intricate food webs. As these core circumstances shifted, the whole ocean ecosystem grew exposed, and the shift arose from an inexorable tectonic shift. The supercontinent Gondwana gradually migrated toward the southern pole. Simultaneously, concentrations of carbon dioxide in the atmosphere decreased, influenced in part by accelerated weathering of silicate rocks and ongoing natural chemical processes. With diminishing CO2, the planet's greenhouse warming diminished, causing Earth to radiate more heat into space. Enormous ice caps built up across Gondwana, bouncing solar radiation away and establishing a vicious cycle of intensified cooling. Within a brief span on the geological timeline, sea surface temperatures plunged around 4 degrees Celsius. As the glaciers grew, shorelines receded sharply by approximately 100 meters. The coastal shelves, which supported the bulk of ocean biodiversity, surfaced or were submerged no longer. Vital habitats for countless species evaporated. Creatures couldn't migrate to profound depths swiftly enough, nor evolve rapidly to cope with the chill and altered oxygen levels. There was no need for an impacting meteor or eruptive cataclysm. Living spaces simply vanished under the weight of life's own demands. This led to the demise of about 85% of all ocean species, one of the most devastating die-offs in the fossil record. The Ordovician extinction stands out because it slew, through indirect means, eroding the basic prerequisites for existence rather than outright annihilation. As waters shallowed, marine flows rearranged, scrambling the spread of oxygen and vital nutrients. Trophic networks crumbled starting from the base. Creatures suited to balmy, sun-drenched shallows found no refuge. The wipeout progressed quietly, in icy, unyielding determination. Fossil evidence indicates this disaster unfolded across at least 2 pulses. The initial wave hit during maximum ice advance, when coastlines sank dramatically. The follow-up came with thawing glaciers and a swift return to milder weather, sparking expansive, low-oxygen dead zones across the seas. Survival, back then, wasn't challenged solely by frost, but by the rapid flip in climate. Neither extreme warmth nor cold alone was fatal. It was the pace of environmental upheaval, outstripping evolutionary responses. Those that bridged the Ordovician divide were mostly bottom dwellers in profundal zones, where conditions stayed steadier and less swayed by tidal shifts. Primitive, ray-finned fishes, despite their basic anatomy, showed greater resilience to ecological pressures than numerous, intricate shellfish. They didn't rule the depths, their variety was limited, yet they endured, and in the grand scheme of evolution, mere persistence frequently suffices. Even amid such staggering losses, this event spared the core of vertebrate development. Rather, it winnowed the web of life harshly, weeding out entities overly reliant on steady environs. From this hardy remnant, key branches of vertebrate evolution branched out in subsequent eras, setting the stage for all terrestrial backbone history. Emerging from this glacial near-apocalypse, a core principle takes shape. Life endures not by evading disaster, but by weathering and rebounding from it. The hardy few weren't mere flukes of fortune, but embodiments of targeted biological strengths, modest needs, robust adaptability, and tight linkage to Earth's core rhythms. From about 372 to 359 million years past, our world stepped into an era where terrestrial advances sparked oceanic downfall. The late Devonian mass extinction arose from an extended sequence of biotic and chemical shifts, representing the inaugural instance where organisms themselves provoked a global meltdown. In the Devonian, seas hosted the pinnacle of life's intricacy. Plated behemoths, nascent sharks, varied cephalopods, and sprawling prehistoric reef systems spanning land masses. Oceanic ecosystems achieved an uncommon equilibrium, topped by top hunters like Dunkleosteus, a plated behemoth exceeding 6 meters that could pulverize skeletons with its jaws. Devonian waters seemed perfected, a realm primed against upheaval, but as marine realms flourished, land masses were reshaping dramatically. Primitive woodlands arose and proliferated. Vegetation evolved beyond ground-hugging carpets, gaining sturdy stems, penetrating roots, and towering heights to seize light. This shift marked a pivotal leap as terrestrial biology first engaged deeply with Earth's rocks via waterways. These flushed minerals into seas at levels upsetting natural equilibrium. The excess sparked rampant growth in plankton and microbes. Initially, the waters buzzed with unprecedented vitality. However, when these creatures perished, the process of their breakdown devoured enormous quantities of oxygen dissolved in the water. Over time, vast sections of the sea descended into oxygen-poor states, and in numerous areas oxygen vanished altogether. Indicators from geochemistry, such as sediments packed with organic matter and distinctive isotopes of sulfur and iron, demonstrate that this oxygen loss extended beyond the deep seas into the shallow coastal waters as well. About 75% of ocean-dwelling species were wiped out amid this extended wave of extinctions. Devonian coral reefs crumbled nearly to nothing and didn't resurgence in fresh varieties for many tens of millions of years. Big, energetic animals requiring lots of oxygen like Dunkleosteus itself couldn't endure in such a choking marine realm. The reign of heavily plated fishes concluded not from rivalry among species, but due to shifts in the chemistry of their surroundings. What distinguishes the Devonian extinction from other disasters is its drawn-out timeline and piecemeal structure. Rather than one abrupt cutoff, it unfolded as multiple successive downturns, each further straining the web of life. Existence didn't evaporate all at once. It was slowly worn away, even as root causes stemmed from developments that appeared advancing in other places. On a profounder note, this event represented the initial instance in planetary history where living things functioned as a driver of geological change. Terrestrial vegetation pulled carbon dioxide from the air, moderated the weather, and formed rich earth. These effects were long considered positive, but that achievement itself first threw the seas into turmoil. Organisms sparked a worldwide self-limiting reaction against their own proliferation. There was no purpose or foresight, just the unavoidable results of natural selection. Tiny seafloor dwellers, needing minimal oxygen, or those tough enough to withstand extremes, persisted in protected biological pockets. Even more crucially, though, a certain category of life forms confronted a groundbreaking evolutionary crossroads. With the seas, the birthplace of all life, growing ever more lethal, remaining put ceased to be the less risky path. In coastal shallows, marshlands, and estuary mouths, lobe-finned fishes like Tiktaalik appeared on the scene. These weren't beings that abruptly stepped onto dry land, but ones that bridged aquatic and terrestrial realms. The Devonian extinction surpassed mere elimination of that era's dominant sea-dwellers. It steered the trajectory of backbone-bearing evolution. Some 252 million years ago, the planet teetered perilously near the ultimate limit for intricate forms of life. Via an extended, unyielding, and merciless ordeal, Earth almost strangled its own vitality. The Permian-Triassic extinction transcended simple species loss. It stood as the most devastating biotic calamity on record, a phase when the mechanisms sustaining life crumbled progressively across the globe. Layers of rock, patterns of species variety, and traces of biology before and after the Permian-Triassic divide, scrutinized over generations, confirm that around 96% of sea species disappeared. Alongside nearly 70% of terrestrial organisms. Primeval coral structures were virtually obliterated. Whole lineages that had thrived for scores of millions of years suddenly hit the wall of their existence. The trigger didn't hail from space. It surged from the planet's inner core. It erupted from the depths of the mantle in present-day Siberia. An immense barrage of basalt outflows, dubbed the Siberian Traps, commenced there. Far from a lone vent, this was an eruption spanning a whole continent, lasting for tens of thousands of years or possibly more. Molten rock inundated millions of square kilometers, and far worse, it spewed massive volumes of carbon dioxide, methane, and sulfur dioxide skyward. With carbon dioxide spiking, the world plunged into a severe hothouse phase, hiking average temperatures worldwide by about 5 to 10 degrees Celsius. Such a rise proved sufficient to disrupt life's equilibrium everywhere. Seas heated up, and higher water warmth slashed their oxygen-holding capacity. Oxygen shortages proliferated, particularly in intermediate and profound depths. Lifeless areas ceased being sporadic. They turned pervasive. Concurrently, carbon dioxide seeped into the brine, spawning carbonic acid and sparking acidification of the waters. Once, the core of ocean food networks buckled. Upper tiers couldn't hold on. Planetary sustenance hierarchies disintegrated from the bottom up, with zero chance of rebound. The Permian extinction's horror lies not just in the death toll's magnitude, but in its all-encompassing breakdown. No refugees endured. Every habitat proved vulnerable. As marine zones asphyxiated, terrestrial ones tumbled in their wake. Vegetation withered away, leading to soil degradation and the collapse of essential nutrient cycles. Essential elements leached into the oceans, exacerbating bacterial overgrowth that depleted the scant oxygen supplies. This created a vicious cycle, with every breakdown amplifying the subsequent ones. In such harsh conditions, big, specialized creatures with lengthy reproduction times faced slim odds of making it through. In contrast, microbes with adaptable energy processing and remarkable resilience survived, keeping carbon and sulfur processes alive. Certain small animal lineages, like ostracods featuring compact bodies and quick generations, scraped by during a time when almost all other life forms perished. On a profounder note, the Permian extinction serves as a grim reminder that our planet isn't inherently kind. Once certain physical and chemical limits are breached, Earth can turn aggressively against the very life it once nurtured. Our world maintains a delicate equilibrium among its geological forces, atmospheric patterns, and living systems. A harmony that can shatter internally. No asteroid required. Still, out of the ruins of Earth's most devastating disaster rose a fresh chapter. With old power structures dismantled and habitats reconstructed from scratch, species primed for a recovery landscape started to thrive. Fresh paths in evolution unfolded, favoring the quickest adapters over past overlords. Approximately 201.3 million years back, the planet reached a subtle but pivotal juncture. This era marked a pivot in life's trajectory, driven not by complete wipeout, but by a realignment of adaptive strengths. The wipeout, closing the Triassic and ushering in the Jurassic, paved the route for dinosaur supremacy. Toward the Triasic's end, Earth remained bound to the supercontinent Pangaea. That enormous landmass extended across both poles, fostering harsh worldwide weather, parched inland regions, erratic shorelines, drastic temperature fluctuations, and habitats in constant turmoil. As Pangaea started fragmenting, the Earth's shell cracked at its frailest points, sparking vast continent-spanning basalt outflows from the Central Atlantic Magmatic Province, or CAMP. Among the mightiest volcanic episodes in Earth's past, it blanketed millions of square kilometers and played out in repeated bursts across hundreds of thousands of years. Far from one big blast, it amounted to a prolonged assault on the planet's climate machinery. Every surge pumped enormous volumes of carbon dioxide and fellow greenhouse gases skyward, thrusting Earth into swift, erratic heating. Geochemical records reveal sharp spikes in worldwide temperatures, upended weather patterns, and swings between brutal dry spells and torrential downpours that wrecked teetering ecological setups. Seized suffered dual blows. Hotter waters cut oxygen capacity, and surging dissolved CO2 spurred acidification, harming shell-building life. This led to the demise of about 70 to 80% of species, gutting much of the globe's biotic framework. The Triassic realm had been ruled by assorted early reptile clans, including hefty hunters from the pseudo-Suchians and varied lizard-like types filling assorted niches. Back then, dinosaurs rated as a sidelined offshoot, sparse in range, modest in stature, and tucked into limited roles. As shifts in the environment surged past a tipping point, survival edges flipped. Bulky, finely tuned animals, reliant on steady food chains and sluggish breeding, turned acutely at risk. Dinosaurs, however, boasted an array of biological perks that proved fortuitously game-changing. Their vertical stance, bolstered by robust back legs, promoted streamlined locomotion and lower energy demands in tough settings. Advanced breathing setups featuring unidirectional lung airflow boosted oxygen uptake in sweltering, low-oxygen air. Oviparous breeding paired with brisk maturation let their numbers recover fast from upheavals. These features positioned dinosaurs to outlast numerous rivals. With leading competitors crumbling, niches yawned wide, from apex hunters to hefty plant eaters. In the ensuing millions of years, as Pangaea kept splitting, fresh land masses took shape, weather varied more by region, and seas expanded. Habitats grew more plentiful and diverse. Amid this evolving backdrop, dinosaurs sparked a burst of variety in shapes and scales. Dinosaurs evolved to fill a vast array of niches on land, from enormous, long-necked plant eaters stretching up to snag foliage from treetops, to swift hunters and tiny, hard-to-spot creatures. They held sway over Earth's ecosystems for about 135 million years, far outlasting all of human existence so far. Following nearly 175 million years of their reign, a pivotal and uncommon catastrophe unfolded in space. At the close of the Cretaceous era, 66 million years ago, a massive asteroid, measuring 10 to 12 kilometers across, hurtled into the planet at over 20 kilometers per second, crashing into the region that's now Mexico's Yucatan Peninsula. The burst of energy in that moment dwarfed any force humans have ever known. In the opening minutes, the ground quaked ferociously, sending shock waves circling the globe with power beyond any quake in contemporary records. Vast tsunamis, towering hundreds of meters, barreled across oceans and demolished shorelines, wiping out marine habitats in mere hours. For months or even years to come, sunlight dimmed sharply, halting photosynthesis, the core energy source for almost all life on Earth, and causing it to fail worldwide. Vegetation perished in huge numbers, sparking a chain reaction that unraveled food webs at higher levels. Studies by paleontologists show that around 75% of species on the planet vanished in the Cretaceous-Paleogene extinction event. The non-bird dinosaurs, long-term masters of the continents, couldn't weather this environmental upheaval. Not due to frailty, but because of their immense size, narrow adaptations, and reliance on steady habitats. Certain kinds might have made it through the first day of destruction, and even the widespread fires sparked by glowing fragments falling back from the sky. Yet as darkness lingered and greenery didn't rebound, their enormous frames and voracious appetites turned into deadly burdens. Smaller creatures, those with rapid breeding, adaptable eating habits, and options for hiding, like burrowers, water dwellers, or scavengers feeding on decay, stood a stronger shot at outlasting the endless gloom.
Tiny life forms, particularly bacteria and single-celled algae, kept essential biogeochemical processes running, averting a total breakdown of biology on the world. This Chicxulub impact compels us to reconsider true resilience in the story of evolution.
a 175-million-year empire, offered no shield when the basics of the environment flipped in a flash of geologic time. Evolution doesn't reward sheer bulk, speed, or terror. It spares whatever can pivot fast to a radically altered reality. In reality, the Cretaceous-Paleogene wipeout marked just a short interlude in the cosmos's vast, stormy chronicle. Life didn't craft Earth on purpose. It simply bent to its whims through luck. The prior 5 great die-offs didn't wipe out existence altogether. Rather, they acted as pivots, reshaping life's realm and driving advancement onward. But today's crisis stands apart. The 6th, mass extinction, kicked off not from asteroid strikes or tectonic shifts, but from human hands. With disappearance rates soaring 100 to 1,000 times above normal baselines. Our species has emerged as the first in 4.5 billion years to unleash a worldwide life crisis through its deeds alone. As vital connections in nature fray at breakneck pace, we're not just gutting diversity, we're eroding the bedrock of our own existence. Still, spanning eons, life's toughness exceeds what our minds can grasp. Should we falter in adjusting to the upheavals we've unleashed, the planet will press ahead regardless. Fresh habitats will emerge, and novel life will sprout from the wreckage of our era. The key puzzle before us isn't life's persistence, but whether, in the unfolding tale of the universe, we'll claim a role or end up as faint traces in rock strata. Ever since Galileo Galilei aimed the first telescope skyward in 1609, we've been on an endless quest for extraterrestrial life. Lately, though, breakthroughs have unveiled wonders, reshaping our ideas of what's out there. A standout revelation from NASA's Cassini probe revealed geysers of frozen water bursting from Enceladus, Saturn's moon, laden with intricate organic compounds, the raw materials for biology. And that's just the beginning. Recent research on potential underground oceans beneath the surface of Europa, that mysterious satellite of Jupiter, bolstered by observations from the Hubble Space Telescope, hints at unveiling secrets of concealed habitats that could harbor life under thick ice layers.
Meanwhile, researchers have pinpointed regions suitable for life on exoplanets outside our solar system, planets such as Kepler 452b, featuring atmospheres and climates reminiscent of Earth's own. We've gathered intriguing hints, yet the core mystery lingers. Is life really present elsewhere? The signs are becoming sharper, and the resolution might be nearer than anyone thought. To grasp where life could thrive, we need to venture past familiar Earth-like settings and investigate radically alien circumstances where fundamental scientific principles could operate in entirely unforeseen manners. When examining far-off worlds, experts first seek out the habitable zone, sometimes dubbed the Goldilocks zone. This orbital band encircling a star offers conditions ideal for keeping water in liquid form, a vital component for life in the forms we recognize. This idea stems from the assumption that biological development demands water, which stays fluid, only within a narrow thermal window. Within our solar system, worlds like Venus and Mars endure harsh extremes, either scorching or frigid, rendering them incapable of holding liquid water and thus barren for life. In contrast, exoplanets like Kepler 452b, a massive terrestrial body roughly 1,400 light-years distant, orbits in the habitable zone of a star akin to our Sun. These types of planets might sustain living organisms, assuming they possess fluid water. But this prompts a profound inquiry. Is liquid water sufficient on its own? Emerging analyses indicate that suitable heat and moisture might not be everything needed for life.
Carbon serves as the core of every intricate organic compound, from proteins to DNA, forming the bedrock of all known biological frameworks.
It enables the assembly of cellular units, life's fundamental components. That's why carbon holds the status of a cornerstone for terrestrial biology. Still, probing for life beyond Earth brings up a pivotal query. Might existence occur sans carbon? Experts are now investigating substitute atoms that could underpin living systems. Silicon, positioned just below carbon in the periodic table, emerges as a prime contender. It forges bonds akin to carbon's, spurring speculation that extraterrestrial organisms could rely on silicon foundations. Nevertheless, silicon's chemical architecture falls short in versatility compared to carbon. Its linkages prove less malleable, hindering the buildup of sophisticated, evolving forms linked to higher life. That said, silicon-dependent biology isn't ruled out entirely. Might organisms flourish in realms profoundly divergent from Earth? A captivating debate revolves around unconventional life forms adapting to bizarre atmospheric setups. Take Venus, for instance, its skies laden with sulfuric acid and ground heat, intense enough to liquefy lead, appear totally lethal. Moreover, potential life could arise not just on planetary crusts but in milder atmospheric strata of worlds with brutal surfaces. Theorists propose that on a globe blanketed by thick air, evolution might occur aloft in elevated clouds rather than down below. There, water could persist unscathed by the searing planetary heat. In pursuit of solutions, investigators have broadened their hunt for signs of life. Beyond hunting for water or oxygen signatures, they're scanning for methane, phosphine, and elaborate organic compounds in remote planetary airs. Such substances might arise from unfamiliar biochemical reactions or signal biological activity. A fresh breakthrough involves detecting phosphine in Venus's upper atmosphere, a compound notoriously hard to generate abiotically, typically requiring life's input. This finding has prompted a re-evaluation of life's prospects in Venus's unforgiving realm. Could organisms distinct from Earth's endure in such a unique aerial niche? Insights from ongoing studies are slowly clarifying this, and these revelations might revolutionize our view of cosmic biology. As we direct our attention to remote worlds in the Goldilocks zone, vast distances, hundreds of millions of kilometers from home, two frozen satellites come into focus. Europa, orbiting Jupiter, and Enceladus, circling Saturn. These frozen realms might conceal one of the most profound mysteries in the search for extraterrestrial life. Each of these satellites possesses a striking characteristic. Under their substantial icy shells lie enormous reservoirs of salty liquid water, settings potentially conducive to biological activity. This revelation represents a groundbreaking and captivating breakthrough, unlocking numerous avenues for scientific exploration. Might living organisms dwell in these subsurface seas? The solution could reside right under the perpetual frost, amid conditions and temperatures that defy our wildest notions. Let's start with Europa, Jupiter's satellite, where observations from the Galileo probe have furnished compelling proof of a worldwide body of water hidden below its substantial frozen exterior, estimated to reach depths of up to 100 kilometers. This subterranean sea might support forms of existence beyond our current comprehension. What sets Europa apart is the presence of fluid, H2O, beneath the surface, a prime prerequisite for biology, despite its remoteness from solar warmth. The puzzle remains. In such a frigid setting devoid of direct sunlight, how does Europa maintain its water in a fluid state? The answer involves tidal heating.
resulting from the gravitational interplay between Europa and its parent planet. During its orbital path around Jupiter, the gas giant's powerful pull generates internal friction, warming the frozen shell and sustaining heat levels in the depths sufficient to preserve liquidity. Vents spewing heated minerals from Europa's seafloor might supply the power for life forms reliant on chemical processes, akin to those in Earth's abyssal zones, where sunlight never penetrates yet. Organisms flourish via geochemical interactions. Hardy microbes could inhabit the ocean's floor, deriving vitality from chemical sources rather than photons. Over on Enceladus, researchers have spotted enormous jets of vaporized H2O, dubbed geysers, bursting forth from fissures around the satellite's southern pole.
Analysis of the ejected material by the Cassini mission not only verified the existence of liquid water, but also revealed organic molecules, including hydrogen, a clear sign of subsurface hydrothermal processes on Enceladus. Such hydrogen suggests that biological activity might be underway in this sea, with methane-generating bacteria drawing energy from these vents. Furthermore, research indicates that Enceladus's waters are alkaline, a pH profile exceptionally supportive of synthesizing primordial organic building blocks. Although Europa and Enceladus paint an intriguing picture of potential biology under their icy exteriors, encountering Titan, Saturn's biggest moon, forces us to overhaul our conventional views on life's possibilities. In contrast to the water-rich moons of Jupiter, Titan upends every established notion of universal biology. Liquid water is absent here, yet another fluid takes its place, methane in liquid form. Titan isn't merely an oddball, it shatters our standard framework for what constitutes life. Is it possible for organisms to thrive in an alternative medium? Methane, rather than H2O. Titan stands alone as the sole satellite boasting a dense atmosphere dominated by nitrogen and methane, distinct from all others in our solar system. Surface conditions on Titan plunge to about -179 degrees Celsius, solidifying water into ice. Yet missions such as Cassini have verified the presence of flowing channels, bodies of standing liquid, and expansive basins across its terrain. Unlike Earth's familiar aqueous features, these are filled with methane and ethane, hydrocarbons that remain fluid only in extreme cold. This setup fosters an alien landscape while introducing a novel take on hydrological dynamics. On Titan, methane in liquid state vaporizes, creating clouds that precipitate back as methane rainfall, replenishing its waterways and pools. It mirrors our planet's familiar evaporation precipitation loop, but substitutes hydrocarbons for H2O. In essence, Titan evokes a chilled echo of primordial Earth, brimming with the raw materials to spark organic precursors, albeit sans water. Complex organics, known as tholins, have been detected on its surface too. These arise from reactions between UV radiation, cosmic particles, and atmospheric gases like methane and nitrogen. Thus, Titan emerges as a singular laboratory of chemistry, evoking an ancient Earth analog minus the wet element. Here, fluid methane plays the starring role in any hypothetical biosphere. On our world, H2O excels as life solvent, adept at breaking down substances and enabling vital reactions. Methane and ethane, being nonpolar, don't dissolve materials as effectively.
Still, in Titan's sub-zero regime, liquid methane could serve as a reliable medium for intricate structures that might underpin exotic biology. To probe this further, specialists in astrochemistry have simulated entities termed azotosomes, perspective barriers akin to cell walls viable in methane-based environs. These azotosomes rely on nitrogen-rich architectures, diverging from the lipid-based membranes seen in terrestrial cells. This opens up an entirely fresh avenue in the field of astrobiology, suggesting that life on Titan might emerge not from water, but from methane and ethane instead. Might these compounds spontaneously form intricate formations that support living processes in a frigid, oxygen-scarce setting? Should life thrive on Titan, it wouldn't rely on oxygen for respiration or water as we typically envision. Rather, such life might harness atmospheric hydrogen and organic compounds to generate power through a metabolic process, unlike anything seen in Earth's creatures. Titan pushes against all our conventional notions of what constitutes life, compelling us to discard the old constraints that insisted on water, oxygen, and Earth-like mild climates as essentials. Probing Titan goes beyond merely hunting for signs of biology. It's an expedition to uncover the true boundaries of existence across the cosmos. How do we verify or disprove the presence of alien life on remote worlds, separated by dozens or even hundreds of light years? The solution rests not in speculation or guesses, but in cutting-edge innovations that grant us a glimpse into the cosmos, scanning for distant indicators of vitality. A major leap in detecting alien biology has come with the James Webb Space Telescope, known as JWST. This instrument functions by scrutinizing light as planets transit the atmospheres of stars in far-off systems. As stellar light filters through a planet's gaseous envelope, certain molecules soak up particular light frequencies. By examining those absorption patterns, researchers can pinpoint the precise makeup of chemicals in that atmosphere. Such techniques enable the spotting of molecular signatures that reveal biosignatures, hints of biological activity pointing to possible life. With its remarkable precision and infrared prowess, JWST equips experts to hunt for biological markers even in the air of worlds scattered across the galaxy, places we've never had the means to visit. When direct trips to far planets aren't feasible, investigating biology in cosmic settings turns crucial. The International Space Station, or ISS, serves as an ongoing orbital lab for space biology, where tests under low gravity and heavy radiation exposure have shed light on how far life can endure in space's unforgiving realm. Among the standout ISS studies is the European Space Agency's EXPOSE program. It involves subjecting extremophile microbes to zero gravity while blasting them with space's cosmic rays and utter vacuum. The findings stunned observers. Numerous bacterial types, including Bacillus subtilis and Deinechus radiodurans, not only endured but multiplied after prolonged exposure to these conditions. These tests bolster the idea of panspermia, the notion that life could travel between worlds via meteoroid debris. If Earth bacteria can weather space's trials, might biology on Europa or Titan have originated off-world or arrived via impacting space rocks? Such inquiries reshape our cosmic worldview and offer vital insights into alien existence. Orbital trials like these deepen our grasp of life's resilience in brutal habitats, paving the way for investigations of comparable worlds. Yet, a vital insight into life's durability is found much closer to home. Actually, Earth's own dwellers in the most brutal locales are yielding key evidence about life's feasibility in alien spots that appear utterly hostile. Thus, is it possible for biology to flourish in wildly extreme conditions we've overlooked? Our planet teems with creatures adapted to what seem like deadly realms. These are extremophiles, beings that not only persist but prosper in scenarios too severe for nearly all other life forms.
Extremophiles upend our ideas about the bare minimums required for survival. Rather than limiting hunts to worlds with steady warmth or flowing water, our quests now include the most punishing terrains. Thermophilic organisms provide a prime illustration. They dwell in scalding geysers where heat soars close to 100 degrees Celsius. In those spots, liquid water isn't life's sole medium. Intense heat and potent acidic processes are what foster biological activity.
Is it possible that life might emerge from hydrothermal vents on worlds like Mars or Europa, thriving in those brutal conditions? Quite possibly. If microbes can harness the chemical energy from such vents, survival becomes feasible. Consider halophilic bacteria, too. They flourish in super salty lakes where salinity levels soar tenfold beyond Earth's seas. This prompts a key inquiry. Might life persist in Europa's buried oceans, thought to be laden with intense salinity? Earth's halophiles have evolved to endure these rigors, offering blueprints for potential alien microbes in comparable settings. A standout case is Deinococcus radiodurans, a bacterium that shrugs off massive radiation doses, thousands of times lethal to us humans, and mends its own DNA when blasted by it. Such resilience positions it as a prime candidate for probing how life might adapt to radiation-bombarded realms, like Jupiter's satellites with their ferocious particle storms. Could alien life forge analogous defenses to brave the cosmos's unforgiving voids? As we probe hotspots of searing heat or blistering radiation for signs of biology, a tale of endurance lurks far below our own seas. The Hadal Zone, the ocean's profoundest depths, crushes with pressures hundreds of times surface norms. Yet there, minuscule creatures like bacteria and tiny crustaceans persist amid the squeeze and desolation. Astonishingly, Hadal dwellers have crafted molecular tricks to shield proteins and membranes from imploding under that immense force. Mitokin, life forms dwell under the frozen crusts of icy orbs like Europa and Enceladus, where vast seas hunker beneath ice sheets, battered by colossal pressures and chill. Researchers suspect that any biology there might echo the Hadal Zone's tenacious forms, far removed from surface Earth's milder climes. Exploring extremophiles and the Hadal abyss not only illuminates survival on our world but broadens our view of existence elsewhere. Breakthroughs in extreme biology have reshaped our cosmic outlook on life's prospects. It needn't cling to staples like liquid water or breathable air. Biology can sprout wherever fluids and energy converge. Lab tests on spacefaring microbes, coupled with Hadal and extremophile studies, reveal life as commonplace, not an Earth-exclusive fluke.
If our planet's hardy species weather such ordeals, then off-world life could bloom in realms beyond our wildest guesses. These puzzles now drive contemporary cosmic quests, evolving from mere theories into mission mandates.
Our hunt for extraterrestrial biology spans uncharted cosmic frontiers, from the iced seas of Jupiter's Europa and Saturn's Enceladus, to spots where methane and organics might dissolve life's building blocks. Meanwhile, tools like the James Webb Space Telescope peer into far-flung exoplanets, unlocking fresh avenues for spotting biosignatures. Fresh findings affirm that biology isn't an Earth-only rarity. This isn't idle conjecture anymore. It's solid proof that life may dot the cosmos widely. Unearthing alien life transcends mere microbes on alien soil. At its core, it's about recasting our identity. Spotting even humble bacteria under alien ice or methane dwellers would show life as no cosmic accident, but a natural outcome of stellar forces and molecular dances. Our voyage presses on, seeking not just biology, but our role in this immense expanse. The quest for life off Earth endures.
What we've uncovered is just the opening act. Still, it's clear. Alien life awaits discovery soon, ushering in fresh eras of unraveling the cosmos's essence and boundless potential. Hey. Overwhelming heat everywhere. Heat crashing in. Heat. Absolutely. Oh, the warmth intensifying way up high. Heat. Hey. Blazing heat. Heat pouring down. Heat. Sure thing. Heat. Endless heat. Heat surging. Heat and more. Heat. Hallelujah. Heat. Glory. Oh, how I adore the sacred. Fine, let's go. Heat. Move it along. Heat. Brimming with heat. Heat. And heat.